All right, so this is Mr. Rollison, and we're going to do a walkthrough on this Unit 4 and 5 exam on Newton's laws of motion and this idea of equilibrium and stuff. So the first question says, think of your drive to school this morning, and you're supposed to think of when you're at equilibrium and when you're not. And basically, it comes down to this, is you are at you're not at equilibrium. Let me start with that. Not at equilibrium whenever you are accelerating, which includes slowing down. Accelerating. So that could be a positive or a negative acceleration if you're slowing down. You are at equilibrium whenever you are at constant velocity. So when you're still, of course, that's a constant velocity of 0, and that seems like equilibrium. But when your car is driving down the freeway at a steady state, that means if you're not accelerating, you must have a balanced force, right? Your engine is pushing forward on the car, and the friction and air resistance and everything else is pushing backwards. So you must have a balanced force. You're either going to have a balanced force and be at equilibrium, or you're accelerating or decelerating, speeding up or slowing down. Those are the only two things. So for this question, you got to think about your car. And whenever your car is stopped or moving at a constant rate, that's going to be equilibrium. And when your car is accelerating or decelerating, braking, slowing down, that's not at equilibrium. And so that's what you got to think about and balance and analyze through the I'm sorry, I'm having trouble getting the board to respond to what I'm asking it to do. As you think through driving to school, whether or not you actually drive to school, you still have to answer the question, okay? I had people on the test say, well, I don't drive to school, so nothing. And that won't do you any good. So, okay, I think I've got that board responding better now. All right, so this question basically has to do with breaking up. You've got a certain amount of force that gravity is exerting on the 28 kilogram block, right? And you're trying to figure out the amount of tension on each cable. So basically, this is going to involve triangles. Most force problems involve triangles and trig functions. So in this one, we know the first thing we have to do is figure out the force of gravity. So the force of gravity is going to be the mass of the block times the acceleration due to gravity. So here's what I'm going to put some different numbers in here for you, so you can go back and take in the test with these numbers, and I haven't actually given you the answer. So for the purposes of this example, we're going to go with 20 kilograms, and we will make these 2 meter strings, and I'll just leave the 3 meter. And it won't, that's enough obfuscation. All right, so the force on our 20 kilogram block is going to equal the mass, 20 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared, which is also 9.8 newtons per kilogram. That's another way to talk about the force of gravity because it's a field force. So that is going to equal what? Now we're going to have to work slow because I don't have these pre-calculated. So it's going to be 20 times 9.8 equals, so that's 196 newtons. All right? So that means these ropes must be supporting 196 newtons. Now, one of the things with this, so they must be, there must be an equal and opposite force of 196 newtons pulling up, right? Correct? Right. So the thing about this is there are two ropes of equal length supporting this thing. So so you just kind of got to know that in this instance, they're dividing the force in half. So what we're going to do is think of this as a triangle. So here's the actual force, and it's going to be 196 newtons divided by 2, because for each string, it's only holding up half of the force. So 196 divided by 2 equals 98. So that's 98 right there. And now I'm gonna switch colors here so we can kind of make things followable. What we're actually wanting to get is the tension on this rope right here, right? That rope right there. So what we're trying to do is we need to figure out the proportions of the triangle. So we have this triangle right here, and the third part of the triangle is going to be the ceiling right there. So the rope is pulling up 98 newtons, and we want to find out the newtons on this thing here. So what we have to do is figure out, we're going to treat 98 newtons like a length, and we got to figure out how long the hypotenuse is for this triangle. So, to figure that out, what we're going to have to figure out is this angle right there. And to figure out that angle, we're going to need to know, what we're going to do is figure out the physical proportions of this triangle, and we're going to use that to calculate the angle. And once we know the physical proportions, then we can figure out what the actual forces are. So we know 2 parts of this triangle. We don't know how long this 98 newtons piece is, but we know that this piece here, is 2 meters long, right? And we know that other leg at the top is going to be 3/2 meters, which is the same thing as saying 1.5 meters, right? And it's 1.5 meters because it's half of the 3 meters that separates the hooks that those 2 things are hanging from the ceiling from. So we got this is a right triangle, and we got a right triangle with a 2 meter hypotenuse and a 1.5 meter leg. And now we got to think back to our trig functions. And I'm sorry, but you just never get away from trig functions when you're dealing with things like force and all that stuff. So we got to remember SO, CA, TOA, right? So that's the sine of the angle is the opposite over the adjacent. The cosine of the angle is the sine of the angle is the opposite over the hypotenuse. The cosine of the angle is the adjacent over the hypotenuse, and the tangent of the angle is the opposite over the adjacent. So we are trying to get this angle right there, and we've got the opposite leg, and we've got the hypotenuse, right? So if we've got the opposite leg and the hypotenuse, that means we're going to want the sine function on that angle. So we know the sine of an angle. Oh, I'm not going to write it. That's kind of hard to see. I don't know if that's going to be hard to see for you, but I'm having trouble seeing it. So here we go. So the sine of the angle equals the opposite over the hypotenuse. So in this case, the sine, and I'm going to use theta because we like to use theta for angles, equals the opposite leg, which is 1.5, over the hypotenuse, which is 2. Normally you can't put a decimal on a fraction, but we're doing it because you get to do that. That's one of the great things about physics as opposed to math. We get to put decimals on fractions and no one's going to yell at us for it. So we're going to go 1.5 divided by 2, and we find out that the sine of this angle is 0.75 degrees. So now the last thing we need to do, and this is where your calculator really shines, is we're going to look for this button. It's usually right above. It's the second function on the sine button, and it's the inverse sine or the arc sine. And what we do is we can put in whatever the sine of the angle is, and it'll tell us what the actual angle is. So we'll go the inverse sine or arc sine of 0.75. Make sure your calculator's in degree mode, and that gives us an angle of 48.6 degrees. All right, and we're getting there. We're almost done, actually. So now we know this angle is 48.6 degrees. This pen is very thick. I wonder if I can make it thinner. I do not see a way to change the size of the pen. That's too bad. Okay, doesn't matter. So now, let's just point out what we know. We know that this is 98 newtons because it's half of the 196 newtons. We know this angle is 48.6. What we don't know is what the actual force is on the hypotenuse of this triangle. So now we're going to use the 98 and the 46 degrees to figure out the hypotenuse. So we're looking for a trig function, back to our trig functions, so, ka, toa. And now we've got, this is the angle in question, is 48.6. So the one we know the angle and we know the adjacent leg. So then we're going to use the cosine function, which is the adjacent over the hypotenuse. And we actually know the opposite leg too, it's 1.5, so we could use either one. What we needed to do was find the angle, and we did. So now we're going to say the cosine of 48.6 equals the adjacent, which is 98, over the force of tension. That's the hypotenuse. That's what we're trying to find right here, is the force of tension on this thing. This is getting to be a really messy board. All right, so what we have to do is multiply both sides by the force of tension and then divide by the cosine of 48.6. So we're going to end up, and I hope I'm not skipping a math step that I shouldn't be skipping, but the force of tension is going to equal 98 divided by the cosine of 48.6. So we're going to go 98 divided by the cosine, 98 divided by the cosine of 48.6. Again, always make sure your calculator is set properly in degrees, assuming you're working in degrees. And that gives us an answer, and this is our final answer, of 148.2 newtons. So to hold up this 196 newtons at this angle, each of these ropes has a tension on it of 148.2 newtons. And they're balanced, so this is 148.2 newtons also. And that is the answer to that question. So I'm going to erase it. I'm going to erase it. There we go. 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 Oh my goodness, this board is driving me absolutely batty today. Okay. Wow. I really have never had the board act this badly for me before. There we go. Okay. Hopefully we can get the mouse pointer back. All right, next question. Let's see, what do we got? We got basically, okay, so it's a 2-question test. So basically what we've got, we're going to analyze this barrel, and we're going to find out if it's going to slide, and if it slides, how fast will it be accelerating? Because it's either gonna not slide because the force of friction is greater than the net force on the barrel, or it's gonna slide, and if it slides, that means it's got a net force that overcame the friction, which means it's gonna have an acceleration in some direction. So the first thing we need to do is pick our coordinate system here. Oh my gosh, I'm sorry. I'm going to try not to continue to exclaim in frustration. So we got 3 vectors, and we're just going to do north, south, east, and west. So we'll start out like this, and we'll put our we'll make this color this vector right there. We'll try and stay roughly that color. So that's 80 degrees, 80 newtons directly east, right? And then we'll make this one, this green color, kind of keep track of it. And that's going to be 70 newtons south of west. So west is to the left, and it's going to be 40 degrees south. So 45 degrees would be halfway between west and south. So it's going to be about like something like that. And that is 70 newtons. And we know that this angle, oh, that's going to be really hard. This thing does not, I wish it had a smaller pen. That's going to be 40 degrees, okay? And let's pick another color for this. And so this one is 30 newtons, and it's 50 degrees north. So 45 is halfway between north and west, so 50 degrees north is going to be about, that's not very straight. Oh well, whatever. So that'll be 30 newtons, and that's going to be 50 degrees north. And so now the process we have to go through is we have to break all these down into their x and y components, which is going to involve the trig. Can't get away from the trig. Might as well write it right up here. So, ka, toa. And we're going to break them down into their x and y components, add up those x and y's, and that's going to give us the net vector that we're adding this vector together to find out what the net force of all these forces are. So let's make a little chart like this, okay? And we'll go back to vector 1, we'll call this vector A. Oh, I didn't quite get the right color. I meant to keep that the same color. There we go. Vector A, closer anyways. So vector A, let's see, vector A. So we're going to call this our x and our y of each force, okay? So vector A has an x direction. The x direction on vector A is 80, because we're doing newtons. So that's 80 newtons. And there's nothing going up or down. It's directly east. And we're going to call that our plus direction. Let's call that our plus direction. And we're going to call this our plus direction for the y. And so there's 0 in the y. Now we have to go, where's our B? It's that green color, right? Hard to see green. It's so glowy. Okay, so for this green one, we have a triangle that looks like this, and it's got 70 there, 70 newtons, and it's got an angle of 40 degrees right there. And so we want to find the x part of this and the y part of this. So how are we going to do that? Well, it's trig again. So we know an angle and we know the hypotenuse, which means that for this, the sine gives the sine of 40 is going to give up. That's associated with the ratio between the opposite leg and the hypotenuse. So that's going to be the y. It's going to equal the y leg over the hypotenuse, which we know is 70 newtons. So that's just going to be 70. Oh, darn. Curses. That's just going to be 70 times the sine of 40 degrees is going to give us our y leg. 70 times the sine of 40 degrees. And so our y leg is going to be 45 newtons, actually. 45, not, is it newtons? It is newtons, that's what we're doing. Okay, 45 newtons. And so the cosine, we can just do the same thing with the cosine because the cosine is the adjacent leg over the hypotenuse, right? So 70 times the cosine of 40 degrees. 70 times the cosine of 40 degrees is 53.6 newtons. 53.6 newtons. So now we can enter those in our chart, and we'll call that vector B. So for vector B, and here you have to, this is the one thing, you need to look back at the chart over here and notice that vector B, the green one, has a negative x, a negative y, right? And it's also got a negative x. If you think about that as the x part, it's going to the left, so that's negative, and the y is going down, so that's negative. So our y, we figured out, was going to be 45 newtons, so that's negative 45 newtons. And our x is 53.6 newtons. So that, oops, dang it, I can't even control this thing. Negative 53.6 newtons. All right, now let's go to our other vector. So now we've got the third vector here, which is this one right here. And we got to figure out the x and the y. Notice that on this one, the y is going to be positive and the x is going to be negative, right? And we know this angle is 50 degrees. And we know the hypotenuse, because that's the force we're trying to figure out, that's 30 newtons. So, same thing, right? The sine of the angle times the opposite leg times the hypotenuse is going to give us the opposite leg, just like before. So we're going to say the sine of 50 degrees. And then we're going to say the hypotenuse is 30. 30 times the sine of the angle. The hypotenuse times the sine of the angle. 30 times sine 50 is 23 newtons. And then the hypotenuse again. And we're doing that. That's because we remember from up here, we rearranged it to notice that the hypotenuse times the sine of the angle will give us the leg we need. So 30 cosine, because that now we're getting the adjacent leg, the x leg of 50 degrees equals 30 cosine 50. That's going to give us 19.3. So again, make sure you're watching the signs. Just look up here, and we notice that this one is positive in the y direction, but still negative in the x direction, right? So it's got a positive y of 23 newtons and a negative x of 19.3 newtons. Now, all we have to do is add those up. Oh my gosh, I am going to just go crazy. All right, So now all we have to do is add those up to get our final vector. So let's see. That green is hard to see. 80 minus 53.6 minus 19.3. 80 minus 53.6 minus 19. Oh, crud. Sorry. I'm tired, man. It's the end of the day. 80 minus 53.6 minus 19.3. That equals 7.1 in the x direction. And we have negative 45 and positive 23. So that's going to give us negative 22 in the y direction. So we'll go start in the middle here, right? And then we'll go 7.1 in this direction. And then we'll go like, we're just drawing a rough figure. So this is 7.1. Sorry about that. And this is 22, negative 22, but we're just going to notice the orientation of it. Believe it or not, we're not that far from done now. This is a big problem. That's why there's only 2 problems on the test. So now we've got this triangle. Oh, and what we have to do is figure out the magnitude, that's r in those, looks like absolute value things, and the angle of this. So I'm going to go all the way over to the other side of the board and make this triangle so it's a little bit easier to see. So this is 7.1 and this is 22. And we're trying to find the length of this and this angle. So the length, we can just use the Pythagorean theorem, which is a squared plus b squared equals c squared, right? Except we're going to take the square root of a squared plus b squared so that we can say the magnitude of r equals the square root of 7.1 squared plus 22 squared. And we'll just figure that out right now. 7.1 squared plus 22 squared equals 534.4. And then we're going to take the square root of 534.4. So the magnitude, the length, which is the force, is going to be 23 newtons. And it's a bunch of decimals you don't have to worry about. Now we got to figure out that angle, right? We know all 3 sides, so we can use whatever trig function we please. I'm going to use tangent just because it doesn't get used that often. We have the 2 sides already, right? So the tangent of the angle, TOA, right? The tangent is the opposite over the adjacent. So the tangent of our angle that we want, we'll call it theta, is going to equal the opposite, which is 22, over the adjacent, which is 7.1. So the tangent of that angle is going to be 22 divided by 7.1. And that's going to equal 3 point. And when you're doing when you're specifically doing the decimal numbers that are the cosine, sine, or tangent, you want to use a bunch of decimal places, like 4, because they're very sensitive functions. So I'm going to go 3.0986. And now we got that in. Remember, we did the reverse on the previous question. Now we're going to do that inverse tangent button. The inverse tangent. So we're going to put in that number, and it's going to tell us what angle would give us that number as a tangent. So we're going to go tangent -1. That's the inverse button. And then we're going to put in 3.0986. And I meant to put different numbers in this problem, but you still have to show your work, and if you show all this work, you're fine. So tangent, inverse tangent, 3.0, oh shoot. Tangent, inverse tangent, or arctangent, it is sometimes called, 3.0986. So that equals 72 degrees. So the resultant force, so that's 72 degrees. So the force, the net force on this barrel is 23 newtons, 70, and look back at, we got to look back at our original thing where we drew north, south, east, and west over there, just to make sure we get the signs and everything right. So it's 23 newtons, and it is 72 degrees south of west. All right? So that's what we got there. 23 newtons, 72 degrees south of west. So that's what we got to remember. And I'm going to write, you can't see where I'm writing it down, but I'm writing it down so I don't forget it. 23 newtons, 73 degrees south of west. Okay? Now, that is, let's see if I can get this stinking board to erase. I'm gonna. Yes. Oh, I wonder if I. Oh, it says I can use a keyboard. Can. Except I can use a keyboard to turn on the eraser, but I can't. Still can't get the thing to erase. There we go. Oh boy. I am just. Alt M for the mouse pointer. Alt E for the eraser. Okay. So the magnitude of the force, which we just did, that was 23 newtons. And the direction is southwest that we did. The maximum static friction available. So static friction is, so friction, whether it's the static or the dynamic friction, is going to be using the same formula, but it's different coefficients, all right? Alt P for pen. I'm going to have to just use up my keyboard the whole time. I don't know not why. My board seems to be getting worse. All right, so we have this coefficient of static friction is 0.08, and then the kinetic friction is 0.06. So there's only two things that matter when something is sliding. It's how much force, how much pressure there is. Okay, I am having a time. How much pressure there is.
You're on campus, please call the front office. Ms. Taylor, if you're on campus, please call the front office.
How much pressure there is between the surface something is sitting on. That's one thing, right? How hard is pressing? If you got something really heavy, it's harder to slide than something light. That's the normal force. Or force normal, as the guy who does the flippant physics calls it. That's the normal force, how much pressure there is between the things that are trying to slide. The other thing is how slidey they are. So that's the coefficient of static friction. The coefficient of static friction. So in this case, we have to figure out the normal force first. So what is the normal force on something? Well, in this case, it's going to be the force of gravity on it. Now, if it's a ramp problem, that's different because you have to include the angle of the ramp in it. But in this case, it's simply going to be the mass times the acceleration due to gravity. So it's going to be 90 kilograms times the acceleration due to gravity is 9.8, which is also newtons per kilogram if you want to talk about the force. So 90 times 9.8. So that equals 882 newtons of normal force, of pressure, of force between this barrel sitting on the ground. Remember, we're looking in this graphic, we're looking at it from the top. 882 newtons of force. Now, to get the force of maximum static friction, remember static is it's a stationary resistance to something moving. So the static friction force is going to be equal and opposite of whatever force is being applied until that force exceeds static friction. Once it starts moving, then the kinetic friction force resists the motion. But the static friction, when we calculate that, that's the maximum static friction available. So here it is, it's the normal force times the coefficient of static friction, and we use mu for that. So it's going to be the normal force, which is 882 newtons, times the coefficient of static friction, which is 0.08. Notice that the kinetic friction coefficient is lower. That's always the case. It's harder to get something moving than it is to keep it moving. 882 times 0.08. That equals 70.6 newtons of static friction. So if the net force on this barrel is greater than 70.6, the barrel's going to move. Now, do you remember what is the actual net force on this barrel? Well, it was something like this, right? It was 73 degrees south of west. And do you remember how what the magnitude of it, how strong it was? It was 23 newtons, right? So if there's a I got issues. You know what? Forget it. 23 newtons. So if we have 23 newtons of force pushing and we have 70.6 newtons maximum resistance force available before this thing's going to start moving, guess what? It does not start moving. So that's, and that was one of the questions. That's not what I wanted. Alternate M for mouse. That's crazy. Okay, so let's see. So what do we get here? The magnitude of the net force is 23 newtons, 73 south of west. In general terms, it's southwest. The maximum static friction we figured out. I didn't realize the notes scrolled with the page. Now that I say that's cool that the notes actually scroll with the page. The maximum static friction is 70.6 newtons. So the answer is no, it will not slide. Now, if just to get the whole thing down here, if this number here, let's see, if here we go. If this number here was less than this number here, let's say this number was 18 newtons, then it would slide. And what you'd have to do is figure out the net force on it. And I'll just keep using this color. Then you'd have to figure out the net force on it. And it would be the force of sliding, which is 23 newtons, minus the force of kinetic friction once it starts moving. And 23 minus 18 is 5. So it would have 5 net newtons of force. And now you're asking if it had 5 net newtons, how fast would it accelerate? and we finally make it back to our good old equation F equals ma. The force divided by the mass equals the acceleration. The net force is 5 newtons, and the mass is 90 kilograms. So the acceleration, if it was in this other case, and this is just teaching now, 5 divided by 90, the acceleration would be 0.05, and that's a repeating 5, so we would just leave that at 0.06 meters per second squared. Not too fast, but that's not much force, is it? So that is the way that goes. Let's see if I can do that. Okay. There we go. I can't believe how many times I had to do that. All right, so now we've got pretty much that's everything, okay? I am gonna stop this video because it's a long video, and I think I've got a ramp problem video somewhere else already in case you want to do that. And that's the whole thing. It was a lot to take in, and the board wasn't as organized as I would like it to be, but it's done, and here it is, and I will send it out. If I can get this thing to pause. Oh, Lordy. Wow, that's really horrible. Can I do it over here?